I
Good.
think so.
Good morning. Assalamualaikum warahmatullahi wabarakatuh. And welcome back, guys. How are you guys? Nobody responding?
Okay, doctor.
Good. Okay. You have already a very long break, which is a week and in break. I hope you guys have done your project or your service learning, and you have already started, kind of finish everything. I hope so, because we are already in our last 4 weeks of the lecture. Okay, so there's not much time left, and unfortunately, we still have to cover two more topics. We haven't even finished distillation yet. Hopefully, inshallah, by today we finish the multi-component distillation. Okay, I'm sure I hope you guys already managed to look up the K constant for your project, which is to use the shortcut method to solve for the distillation column in the mini project. So I hope you managed to get that, at least that part done, and at least find the boiling point, the dew point, all that. Okay, excuse me. Okay, we stopped last time. Excuse me. We stopped last time when we were looking at multi-component distillation. We started by looking at the introduction, and we did part of the beginning part of 11.72, if I'm not mistaken, 11.72 of the example. Yeah. We managed to find the boiling point, the dew point of the top and the bottom product. The bottom product supposed to have a certain boiling point. We managed to get that done. We managed to find the dew point of the top product, which is the distillate. We managed to find the the composition of the distillate and the decomposition of the bottom product. We stopped when we managed to get the minimum number of stages. We stopped there. So today we're going to continue with the rest of the shortcut methods, where we need to find the minimum reflux ratio, the feed location, and the number of stages for that distillation, for that example. Okay, so let me record. I'm going to I'm going to share my iPad. Don't tell me it's pretty slow. Don't tell me it's nothing happening. Oh, hold on, sorry. Okay. This is the example we were looking at before the 1 week break. We have a feed that is at its boiling point. Our composition of the feed is given. We have component A, which is, in this case, the component A is butane and butane. Component B is N-pentane. C is N-hexane. And lastly, D is N-heptane. They are arranged in the least volatile is at the very bottom, in the decreasing order of volatility. Okay, so they are arranged in the decreasing order of volatility. The highest boiling point will be component D. Okay, in this example, your feed, there are a mixture of 4 components. It is specified that 90% of B will be recovered in the distillate. We're just going through the statement. And 90% of your component C, which is that of N-hexane, will be in the bottom. So if you notice that A is not given, the distribution of A is not mentioned at all. The distribution of D is not mentioned at all. It's just specifically for B and D in C. So from there, you already know which one is your light key, which one is your heavy key. Okay. So the split is between B and C. And we already managed to find the dew point, which is 67 degrees C, after we have calculated the composition of the distillate. Okay, the composition of the distillate based on the distribution of B and C given, and we assume that all of A will be in the top product, which is the distillate, and all of D, which is the least volatile, will be in the bottom. So there is no D at all in your distillate, okay? And all of A will be in the top product. So we already managed to get the composition based on that assumption. And from that assumption, you managed to find the dew point, which is 67 degrees C. Based on the K value you obtain from this graph, your K constant, which is in from the textbook. I forgot the figure number. Okay. So from that distribution, you get your from the distribution of the composition, you get your dew point. I'm going through it very fast. And from the dew point, you will get, once you manage to get the dew point, the correct dew point is done by trial and error. We have done it. You will get the equilibrium composition that is in equilibrium with the liquid composition that is in equilibrium with the gas from the top product. So we have done that. And next we did the method to get the boiling point of the bottom product. Again, your composition of the bottom product is based on trial and error, whereby you assume that none of component A will be in that bottom product, and all of component D will be in the bottom product. So based on that assumption, this is your composition. Sorry, that is not your composition. Sorry, the composition is over here. And based on that composition, you will assume a certain temperature for the boiling point. And it so happened that the assumed boiling point of 132 degrees C is the correct value after trial and error. And once you manage to get the correct value of the boiling point, you will get the composition of the gas, which is in equilibrium with that of the liquid. Okay, we have done that. Next, what we did, we calculate the minimum number of stages based on Fensky equation. So we calculate the minimum number of stages based on Fensky equation. You can use either one of these equation, is still the same thing. You can use the log log or natural log. As long as the denominator and the numerator is the same, the equation will give you the correct answer. Okay, so you have the relative volatility of the light key, which is an average value, which you can get from the relative volatility from the top distillate product, from the distillate, and the relative volatility of the light key from the bottom temperature. Okay, the top temperature is at the dew point, the bottom temperature is at the boiling point. So you can get both of these values, okay, at the boiling point and the dew point, and then you get the square root of it, and you get the average value, which you substitute over here. And the rest of it is based on the composition that you assume earlier for the light key. The light key you don't need to assume. The heavy key you don't need to assume, because they are already mentioned. The distribution is already mentioned, so you don't have any try and error. The answer here is still the same, because they are not the same actually, because it's also based on the assumption, because A is not mentioned at all, D is not mentioned at all. So the composition of the light key and the heavy key is still will be different, meaning it depends also on the distribution of A and D. So your N mean is based on that assumption earlier. Okay, once you have got your N mean, your minimum number of stages, then you can calculate your distribution of the other two components. Okay, once you get the distribution of your other two components, then you will get the actual composition of your light key and your heavy key. But that's not, the differences is not that much. Because 90% of 90% of the light key is going to be in the distillate, 90% of the heavy key will be in the bottom product. So the major part is the B and the C, because they're 90%. The component A and D is very trace in a very trace amount. So the distribution will not go too far off from your first initial assumption. Yeah. And now we will continue with the rest of the example. And now let's show what we have got last week. This was our assume the top here, the top table. The table at the top is the assume composition, and the bottom bottom table is the revised version, the revised this composition after we have done the distribution, okay, based on the N mean value. So as you can see, there is slight difference in your light key and also in your heavy key. Only very small difference. Very small. Same for your distillate, for your light key, for your heavy key. As I mentioned just now, because the major part of it, the 90% is for the light key, the 90% is for the heavy key. So the distribution will not be too far off based on the assumed value. Okay? So just very small, very slight difference. Okay? So now we're going to proceed with the rest of the calculation. You're going to calculate the minimum reflux ratio that you're going to use for the distillation. And in order to do that, you will use Underwood method. Okay? Underwood method, you assume that the flow rate is constant. Okay? And you will use the average relative volatility. At what temperature it is at the average temperature. The average temperature is the sum of the dew point with the boiling point divided by 2. So the boiling point that you obtain at the very beginning of the example and the dew point that you obtain at the very beginning will be used here to get the average temperature. At that average temperature, you will get your relative volatility. Yeah. You will get your relative volatility at that average temperature. And how do you calculate your relative volatility? If you recall back, relative volatility is, for example, for component A, the K constant of component A divided by the K of the reference component. You can, in this example, the reference component is that of your component C. So it will be Ka over Kc. K is your equilibrium constant. Okay, so you will get this relative volatility at the average temperature, which is the average temperature of the dew point at the top and the boiling point at the bottom divided by 2. So how to get the minimum reflux ratio? First of all, you need to determine this value, which we refer to as alpha here. Alpha must be determined first from the top from this 1 minus Q equation first. Yeah, and how to know what alpha is done by trial and error. And that value must be between the relative volatility of your light key and the relative volatility. There's an error in the sign of your heavy key. This sign should be greater than but less than. This should be less than. Greater than but less than. There's a typo error there. It should be greater than the relative volatility of your light key, but less than the relative volatility of your heavy key. Okay, now In order to find it, you have to do it by trial and error method. Okay. Once you manage to get your alpha, then you use it to calculate, let me see. You use it to calculate here. Sorry. You use it to calculate your R-min. Once you manage to get alpha, you use it over here in the second equation to calculate your R-min. So in order to calculate R-min, you need to get the value of alpha first by trial and error. And then you can calculate, once you manage to get alpha, then you will calculate your R-min directly. There's no trial and error to calculate R-min, but you get, in order to get alpha, you need trial and error. So let me erase this and continue with the example. Okay, so I'm going to copy first the equation that we need. This is the example just now. We already know that the dew point is 67 from our previous calculation. We already get the boiling point, the actual boiling point. So we get the average temperature, which is the average of these two temperatures, and that happened to be 99.5 degrees C. So you're going to tabulate your component at that temperature. Okay? So this is your table. This is your feed. This is your distillate composition. And this is your bottom product composition. You have to put them there because you're going to put it the values over in order to calculate your R-min. Over here you need your feed composition. Over here you need your distillate composition. Okay, but you don't need the bottom product composition, but it's just listed over here. Okay, now your K value, you're going to get it at this temperature, the average temperature. Okay, once you manage to get your K value, you calculate your alpha, which we have mentioned is equals to Ka for component A is equals to Kc for this example. Okay, so at the temperature of 99.5 is almost 100 there. That is my temperature of 99.5. Okay, at this temperature. For every component that I have in my example, I have component A, B, C, and D. At that temperature, I will look up the K value. Okay. For every component that is given, I will look up the, I will read off the K value from the graph. And I will list it down in my table, which is over here in this column, on the very left column, this column. Okay. So that's my value, which I got earlier, for example, for component A, B, C, and D. These are the values that I got from the graph. And from that K value, I'll calculate my relative volatility, which is that value, based on the equation over here, okay, which is based on this equation. So my Kc should be 1. Should be 1. There's no way Kc is going to be different, and this is going to be other than 1 because the reference component is C. Okay, so Kc should alpha C should be 1, not Kc. Oh, sorry, alpha C should be 1. The relative volatility of C. Now going back to my equation, I'm going to paste the equation. I'm going to paste the equation here. Now I'm going to get this. Oh dear. I'm going to read off, I'm going to get the value of the composition from this column for every component. So that means I have plus, okay, sorry, not plus, equals. I have component A, alpha A, X, F A for component A, alpha A minus theta. I'm sorry, this is theta, okay, plus alpha B, X, F B. I have alpha B minus theta, and I do for the rest of them until I got the last component. Yeah. So if I do that, I will, for example, for component A, this is component A. Okay, component A, then this will become 0.4. Okay. Alpha A is this value, 5.2. Okay, at the average temperature of 99.5, so that is alpha A is 5.2. Over here is also 5.2. The only unknown is my theta. I do the same thing for B. If I look at B, this is my fit composition of B. Okay, and this is my alpha value of average value of for component B. So I'll just substitute that inside this equation. My alpha B is equals to 2.3. My fit composition for B is 0.25. That is the exact value that is given in the statement of the example. This is 2.3, which I got earlier after calculating it. After getting the K value, I calculated the alpha value. So again, the only unknown is your theta. And you do for the rest, the sum of your right-hand side should be equals to 1 minus Q. And what is Q? Q is based on the fit condition. Your feed initially saturated liquid at its boiling point, at the boiling point, at the temperature of the boiling point. So if you recall back, Q is equals to 1 when it is at the boiling point. This is the same as when you were looking at binary component. Q, that is at its boiling point or saturated liquid. Q is equals to 0. You have a saturated vapor, or when it is at its dew point, or you have a saturated vapor. Q, it will be between 0 and 1 when you have a mixture of liquid and vapor. So you have to recall that back, which we have done earlier when we were looking at binary distillation. So in this case, your Q is going to be equals to 1 because your feed is at its boiling point, saturated liquid. So now you just calculate 1 minus 1, that turned out to be 0. So the sum over here, the summation over here must be equal to 0. That is how you manage to get your theta by try and error. Okay, so let's look at the solution. Okay, so just like I mentioned just now, this is how it's done. This is component A. This is component B. You do the rest for C and for D. Okay, for D, the composition of the feed is 0.15, that's 0.15. The volatility 0.467, that's the volatility minus theta. And 1 minus 1 is equals to, oh dear. Why is it 0? I have made a mistake here. Let me check my feed condition. Is it saturated liquid or is it saturated vapor? Let me go back to the problem, to the example, sorry. Somehow I have made a mistake there. It must be typo error. Okay, it's its boiling point. The feed is at its boiling point. Okay, so let's recall back what we have studied for Q. Where is our Q? Let me go find Q. Yeah, this is Q. Okay, Q. Q is equals to 1 when it is what? Liquid at its boiling point. I just want to verify the fact that Q is equals to 1 when your the feed is at its boiling point. Okay, Q is equals to 0 when your feed is saturated vapor, or the feed is at its dew point. So now let's go back to our example. Now where is that part just now? Q should be equals to 1. You have to remember that Q should be equals to 1. I have made a mistake there. I think it's a typo error. There you go. This here. Should be equals to 1. Please correct it. So for 1, this one equals to, the answer should be equals to 0. Okay. So by try and error, this is how it's done. You make a table. You tabulate the assumed value of Q first. Theta. The theta value you assume is between the light key and the heavy key. The relative volatility of your light key, your relative volatility of your light key is this 2.3. Yeah, let me undo that. Let me use a different color. You guys, please correct the mistake, the typo mistake here. Please correct this part. Okay, correct that part. Q should be equals to 1. So the relative volatility of your light key is 2.3. The relative volatility of your heavy key is 1. So your theta should be anywhere between here. Anywhere between that two values. Must be greater than 1 but less than 2.3. So now the author assume a value of 1.21 first. Calculate the sum, this value, that value, the summation, calculate the summation. And the answer is equal to 0.022, quite close to 0, but not yet 0. Now, the author next make an assume value of 1.2, and it's happened to be, the summation happened to be negative 0.05. So the author now, the theta value now is anywhere between these two values. You can do the interpolation in order to get 0, or, you know, I think this is done by interpolation. The final value, 1.2096, is done by interpolation, and it so happen to be very, very close to 0, 0.0001. That is the final value of your theta. This is your final value of your theta. Okay. Once you manage to get that value, you will substitute it inside the equation, which is this equation for the second equation here. Okay. Use that theta over there. From there, you will use the composition of your distillate, which is from this tab column. Okay, the composition of the distillate from that column. The alpha value is still the same. The alpha value is still at the average value, which is that. That is your relative volatility at the average temperature. So now the only unknown is your Rmin. Your theta, you already managed to get it from the previous trial and error method. That is from the sum, this part. Okay, so now let's continue. I'm going to paste the equation again over here. Okay. This is the equation. So I have it over here, the equation too. So let's write down for every component. I have my composition for my distillate there. Yeah, so for component A, 0.6197. And the theta value, the alpha, the relative volatility, 5.2. And the theta just now that I got over here. I'm just substituting it inside this equation for every component. So the sum, you should be able to calculate the sum after because everything is there. The equation is complete for the summation. Okay, so you should be able to get the value of the summation, okay, which is that value, 1.395. Because everything is there, you can do the sum, and the summation is equal to 1.395. So the only unknown left is your Rmin. We can solve for Rmin, and that happened to be 0.395. That is your Rmin. So that is your minimum reflux ratio. And normally the column will operate between the actual reflux ratio will be 1.3 to 1.5 Rmin. Between that range, the optimum reflux ratio, the actual reflux ratio. Okay, so it could be anywhere. The reflux ratio could be any value. It can be any value, but the optimum is normally 1.3 to 1.5. Okay, so time by Rmin. Now, based on this example, I'm not sure what is given. Let's see what is mentioned. What Rmin is going to be used. Sorry, not R. Now, what is R? The actual R. This is the problem. Is there any mention of the actual? Okay. This is only up to part C. Where is part D and E? Should be a continuation of the example. We managed to get Rmin, so the next step will be to get the actual reflux ratio. The column cannot operate at Rmin. Where is the other? Okay, there you go. The column is operating at 1.5 times Rmin. So the actual reflux ratio will be 1.5 times by that Rmin. This is the value of your Rmin. So you multiply with 1.5, you manage to get that value for your actual reflux ratio. Now the next step of the problem will be to get the number of stages and to get the feed location, the plate or the feed location. In order to get the number of stages, you will use this graph. If you look at this graph, I'm going to undo that. If you look at this graph, this is N min. We already managed to get that earlier. We used Fensky equation to get N min. Let me go back and show you guys where we get our N min, our minimum number of stages. Okay, there you go. Our minimum number of stages is 5.404. That's the value that we got using Fensky equation. So that's 5.404. You're going to substitute it in the graph and calculate the x-axis, your x-axis. But you cannot calculate your x-axis, sorry guys. You cannot calculate your x-axis because that value n, this is your actual theoretical stages. You don't have that yet. That is what you need to find, the actual number of stages. You don't have that value yet. So you're going to get it from the graph. Yeah, so now what you have is R min. You do have R min just now. Yeah, you get that, this equation, you calculate this equation in order to know which curve you're going to use in this example. And then you're also going to use the calculate the y-axis R over R plus 1. You do know what is R because the statement said that your actual R is close to 1.5 times R min. So you already managed to get R min. So let's do the calculation. Your R min, we got that value. Okay? And your actual R, we already mentioned that it is 1.5. We already got that value over here. So you calculate your R over R plus 1, you get that value. You calculate R min over R min plus 1, you will get that value. Okay? So using these two values, you will use the graph. What do I have? My R min divided by R min plus 1 is 0.28, roughly 0.28. So where is 0.28? It's below 0.3. So I'll have a curve somewhere there, 0.28, somewhere there. Okay, this is 0.2. So this is going to be 0.25. My next curve is above it will be 0.3. So anywhere close to 0.3 is about roughly is an estimate of 0.28. So, and my R over R plus 1, for my y-axis, I got a value of about 0.37. For my y-axis is 0.37. That is about somewhere there. That's 0.37 because this is 0.3, this is 0.4. So putting the 2 points together where the intersection point is, okay, my curve at this is about 0.28 and my y-axis is 0.37. Where the point of intersection is, I will get the value of n min divided by n. And it so happened to be, if you zoom up, it's roughly close to 0.5, somewhere close to 0.5. This is about 0.45. So it's somewhere about close to 0.5. I'll give it a value of 0.49. Okay, so that will be 0.49. My n min earlier we managed to get 5.404. That's my value for my minimum number of stages. And the only unknown left, the only unknown that we need to solve for is the actual number of theoretical stages. This is the actual number of theoretical stages. So you can get that after you have managed to get the value of your x-axis. Okay? So now, if you solve for that, you will get, let's look at the solution, the answer. Where is the answer? There it is. Okay? You will get the 11 number of stages, theoretical stages. Still theoretical, not the actual stages. You need to know the efficiency of your plate or your tray before you can get the actual number of stages. Once you manage to get that, you have to write it in this form because one of the stage is going to be a reboiler. So you have 10 tray or plates plus one partial reboiler. But if you write this form is still fine. is just referring to stages. Yeah. Next, and before that, going to the feed location. Any questions? I've been going through this example without asking you guys. Have you any questions for me? Guys, any questions? Or I'm the only one that is going through the example. Are you with me?
Yes, doctor.
Good. How about the rest?
Okay, doctor.
Okay, because you guys need to know these steps in order to do your mini project and also for your final. Your final is going to be multi-component distillation. Your second test is going to be just binary distillation. Yeah? Binary distillation is the easiest. And now let's continue. Since you don't have any questions, we will continue with the feed location. Sorry, the feed location is at what plate? And now you already know what is the number of stages. Definitely, your feed location is going to be anywhere between these 11 stages. Okay, so between 10 plates, sorry. 11 stages, but it will be on the number 10 or number from 1 plate to number 10 plate anyway. So how to go about that? You're going to use this equation, Kirkbride, not Kirkbride method. Okay, Kirkbride method, which is using this equation. So let me copy that equation. Okay, let's go through the equation. This is the number of enriching section. Subscript E is for enriching. Subscript S is for stripping. So if you total it up, the number of stages should be number of stripping section plus number of stripping sections should be the number of theoretical stages that you just obtained just now. Should it be number of theoretical stages or should it be number of plate? Somebody answer me. Should it be stages or should it be plate?
Stages.
You sure? Anybody else want to give it a different value?
Stages.
Stages. Everybody says stages.
Yeah, because the reboiler, if you were to consider the plates.
Reboiler is not considered a plate. It's a stage.
Yeah, I mean, if you...
Okay, let's look at the solution. Okay. Sorry. Okay. Okay. So that is stages. Okay, guys. So let's continue. The actual number of stages is 11. So the number of stripping section plus number of enriching section should be equal to number of theoretical stages. So now you have two equations. This is one of the equation. This is the second equation. You will solve it simultaneously. Okay? So let's look at the first equation. What do we have here? If you're going to use natural log, this will be natural log, that will be natural log. Both of them should be the same. If it's going to be log, both sides. Okay? So what do we have here? This is your heavy key composition in the feed. That is your light key composition in the feed. This is the flow rate of your bottom product. That is the flow rate of your distillate. And this is your composition of the light key in the bottom product. And this is the composition of your heavy key in the distillate. Remember, to the power of 2. And so we will look at this example. We will apply the two equations for this example. And now the example is 11.73, a continuation of example 11.72. So remember, this first column is the composition of your feed. This is the distillate composition. This is the bottom product composition together with the flow rates. You have the flow rate for the bottom and the distillate and the feed. So now you will need that flow rate for the bottom and the distillate. So your bottom is 35. That's your distillate. That's your bottom flow rate. This is your distillate flow rate. So you can substitute that inside the equation. For your heavy key in the feed, this is your heavy key. Oh, let me undo that. This is your heavy key. So this is the composition of your heavy key in the feed. That's going to be 0.2 there. Okay? For the light key in the feet, 0.25, that's 0.25 there. So which is, we have already substituted there. Okay, that's the flow rate that we just mentioned earlier. Now, for the next column, the next bracket, the light key in the bottom. The light key is B in the bottom. That is 0.0704. That's that value. And the heavy key in the distillate, that is 0.031. So that's 0.031 to the power of 2. Everything is there. If you're going to use log, then both sides will be log, multiply it with 0.206. This whole thing will be 0.07344 is equal to that value. So you get the inverse of log, you will end up with this part of the equation. And E is equal to 1.184 times by NS. I hope you know how to get the inverse of log or ln. Okay? I hope you guys you are familiar with the calculator on how to get the inverse. So now you already managed to get this as your first equation. And the second equation will be this, where NE plus NS is equals to N. This happen to be 11 stages for this example. So now you substitute that first equation inside this equation. Okay, that will become 1.184 NS. So the only unknown now is NS. So you should be able to get your answer for NS, which is the number of stripping section, which is 5. Okay, and for your enriching, once you manage to get your stripping section, you substitute it inside this equation, you will get your enriching section. So now, where is your feed tray? Your feed tray should be referring to your enriching section, because enriching section is from the top. So your feed tray will be tray number 6, which is that from the top. You should write this full statement from the top, because you are referring from the, you are looking at the enriching section. The enriching section is from the top to the feed. So your feed tray is tray number 6 from the top. Okay, so that is how you locate the location of your feed tray. Any questions? So for your mini project, you have to do these whole steps from the beginning till you get the number of stages and where is the location of your feed. Just the shortcut method. We're not going to go to the rigorous method. That will be done in your final project, in your design project. Any questions?
Doctor, I have a question.
Yes, please.
For the stripping part, if you get the if you do the equation, if is 5.032 something, but doctor, let's say if my NS is get 5.5, do we need to like 5.5 we just round off and we get 6 like this, or we just take 5?
Okay, when you do the calculation in the two equations, you stick with 5.5 first, you substitute it there, okay? And then you calculate your NE. And if your NEs happen to be, for example, a decimal point, then write that value of, for example, 6.4. For example, okay, let's put it 5.4, for example, or 5.5 or so. Write it, fit is equal to tray 5.5 from the top, but actually it should be tray number, just write 5.5 because we this is theoretical. Okay, it's not actual yet. It's not yet actual. It's theoretical. So write down 5.5 then. For example, because 11 minus 5.5, that should be 5.5 also, isn't it? So that is an S. This is an E. So write down here tray number 5.5 from the top. Okay, because this is theoretical. It's not actual. Once you know the actual, then it will be round off figure. Okay, does that answer your questions?
Yes, doctor. Thank you, doctor.
Any other questions? I mean, all of you okay with the explanation? Okay, since we have a few more minutes before we time's up. Let's look at one of the problem at the back of the chapter. 11.77. I gave you an assignment 11.74 that you would need to hand in e-learning. The deadline I forgot already. What I got it the deadline in e-learning. I forgot what was the deadline. So you need to refer to e-learning. Let's look at this problem. I'm going to just briefly go through it because it's going to be a long example. Problem 7.7 at the back of the chapter. In this example, we have a liquid feed. Okay, your feed is going to be liquid at bubble point. And it's going to be distilled in a tray tower. We're going to have this composition. So let me do the table. I can't get a straight line yet. Okay. Oh dear, not doing a good job there. Let me copy that. Those of you guys that already have that do have the textbook, please refer to this problem. This is going to be a short explanation because it's a bit slightly different from the example. That's the reason why I want to go through it. I have how many components? A, B, C, and D. Again, I have 4 components, so I need more than I need, let's see, A, B, C, D. One more line. Okay, done. Now I'm going to copy that. That's for my component. I'm going to do the rest for the feed composition. Feed composition. For the flow rate, the feed, and I'll do the same thing for the distillate composition and for the distillate flow rate. For the bottom product composition, and lastly for the flow rate of the bottom product. That's straight. It doesn't look straight to me. Okay guys, it doesn't look straight. Okay, let me try to get it roughly straight. Yeah, let's do it. Let's write this is component A, B, C, D. Okay, it's not mentioned what are the components. It's just A, B until D. And the composition of the feed for component A, 0.047 as XF. Okay, so for the XFF, what is the amount of the flow rate? We don't know yet. XB, 0.072. C, 0.881. XD, only if there's no D, it's only ABC. Sorry guys, I don't need the last row. It's only until C. Okay, now XD 0.16 for B 0.1913, C 0.687. XW for component A, 0.001 for component B, 0.999. So this, I will erase this. That should erase. Okay. That will be summation. Will be 0.0, 1.0. Okay. XD times by the distillate, XW times by W. There's no mention at all. And I have another one more column. I need one more column. I need one more column because I need the relative volatility. I should have write it the column next to the component should be the relative volatility. So I don't know how I'm going to do this. Let me see. I need to cut it first. I'm going to cut this part. Cut it. Okay. Now I'm going to bring this over here. I have my relative volatility here. Going to press. There you go. I have both. Okay. I think I got wrong. Should be one more. Okay. There you go. Now I'm going to extend this. Extend it. I already got it wrong. Okay, now I'm going to have to draw myself another straight line. I'm not going to be so particular about that, but this is roughly how it's going to be. Okay, guys, so this is my relative volatility. So what I have over here for component A is 4.19. For component B is 1.58. And for component C is 1. So guess what is the reference K equilibrium constant? Sorry, what is the reference for the K equilibrium constant? Yeah, correct, equilibrium constant. Which component is the reference component? Anybody?
Component C, doctor.
Yes, component C. Okay. So now we are not given the flow rate here. Oh yes, we are. For part A, if the feed rate is 100, if the feed rate is equals to 100 unit is mole per hour. Okay, if the feed rate is 100, so you will know what is the feed amount in your feed for component A. That will be 47 based on the composition D here. You know it's going to be 47 because your feed is 100. Flow rate, the flow rate of your feed is 100. So this is going to be 72 and this is going to be 88.1. Is that correct? 4.7, isn't it? Yeah, 7.2, sorry, 88.1. Thank you. Okay, that will give you 100. Okay, so now based on this, you can do the rest of the calculation. For example, feed is equals to the total flow rate balance, the total balance. Feed equals to the distillate plus bottom product. So you have to imagine the column itself. Okay, for the component A, do the component A balance. XFA is equals to XDA D plus XWA W. Okay, so what do you have for component A is 4.7 for your feed, that's flow rate. For your distillate, you know, it's 0.126. That's the composition here, but you don't know the flow rate of D. And you do know the flow rate or the composition of your bottom product for component A, that's equals to 0. So that's 0. So from there, you can calculate what is D, isn't it? 4.7 divided by 0.126. You should be able to get your D. So once you manage to get D, you should be able to calculate what is W based on this first equation. Okay, so once you have done that, you should be able to fill up the rest of the table over here. Over here. Should be able to do that because you know that your distillate is what? Based on the calculation here. And what is your W? Or you should be able to do fill up the rest of the table. Okay, so that is for the first part of it. Calculate the flow rate for your distillate and the bottom product. So let me give you the answer. What do I have? Let's see. When you do the calculation, 4.7 divided by 0.126. The answer is equals to 37.342 roughly. Solution on the solution is a bit different. Yeah. Well, one thing for sure, what I can say is this. Okay, what I can say is this. None of your component A is going to be in the bottom product. Okay, none of your component A is going to be in the bottom product. So that means all of your component A will be in the top. So 4.7 will be 4.7 over here. That's what you know. There's none of it here. That's what you know. And the rest will be depend on the metal balance. But I'm surprised that the answer in the metal balance is a bit different from the one that I just calculated. Let me check. 0.126 times by D is equal to 4.7, obviously, isn't it? So D is equal to 4.7 divided by that, isn't it? Can you see any mistake that I've done here? From component A I already know how to get the distillate, isn't it? Distillate flow rate, which is 37.03. The solution, 37.315. It's a bit different from my answer, 37.302. The solution gave me a value of 37.315. Well, I don't know why is there a difference, but let's continue. 37.3, it's about roughly the same, 37.3. But I don't know why is there 37.315. But let's continue. Just one decimal places. There's W. Therefore, equals to 100. Therefore, your bottom product is going to be 100 minus 37.3. What is that? I got 62.7 1 per hour. Okay, write down your unit, these guys. You have to write down your unit. That's 62.7. Yeah, so you kind of know what is going to be the rest of the values in the cells in the table. So you should be able to calculate that. And next, for part A, you need to calculate, oh my God, I have roughly a brief explanation then. For part A, you need to calculate the number of stages at total reflux at R equals to infinity. What is N min? Yeah. For part A, we need to calculate this distribution, concentration of A in the bottom. Concentration of A in the bottom. Okay, guys. The way I understood the problem is that initially this is the assumed distribution of A, because B and C is already is the heavy key, the light key, and the heavy key. So component A is assumed to be all of it to be in the distillate. So none of it will be in the bottom product. So now, once you manage to get that and mean, you should recalculate the distribution of A in the bottom product and in the distillate. You should recalculate, okay? And now for part B, the continuation of that problem, calculate what is R mean and the number of stages when R is equals to 1.25 R mean. So just like we discussed just now how to calculate R mean, you need to get the theta first, which is between the relative volatility of the light key and the relative volatility of the heavy key. So you already have these values here of the key of the relative volatility. You know that it should be between the light key, which is your light key. Your light key is happening to be, so happen to be, for my understanding, this is your light key, this is your heavy key. So it should be between 1.58 and 1. So your theta should be between that value, 1.58 and 1. So you have to do it, try and error to get your theta. Once you manage to get your theta, solve for Armin. Once you manage to get Armin, get the number of stages and the feed location, number of theoretical stages. That's how we discussed the example 11.72 and 11.73 just now. Any questions? Any questions? Hey guys, I don't want to keep you any longer because the time is already 11:01. You have your next class to go to. So thank you very much. We will look at a new chapter this coming Thursday. Okay, and you can now start to do your mini project and also the assignment. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Doctor.